Welcome to The Explainer. Today we're going to peel back the layers of software to get right down to the metal. We're decoding one of the most fundamental layers of computing, assembly language.
So, how do you talk to a computer in its native language? It's a simple question, but the answer is pretty complex. Before we can tell a computer what to do, anything from opening a browser to launching a rocket, we have to understand how it thinks. And it doesn't think in words, it thinks in a relentless stream of electrical on and off signals. Basically, in numbers.
And this is what it looks like. Raw binary machine code. It might look like total gibberish to you and me, but this is the only language a processor truly understands. Every single action your computer takes, from the simplest little calculation to the most complex task, it all boils down to a sequence of ones and zeros, just like this.
And that brings us right to the fundamental problem of programming. Trying to communicate complex ideas using only ones and zeros is, well, for us humans, it's incredibly difficult. It's dense, it's abstract, and get this, a single misplaced bit can cause the entire program to just fail.
Here's an analogy for you. Imagine trying to navigate a city, but every single instruction is just a long string of numbers. No turn left at the big oak tree, just proceed to latitude 40.7128, longitude minus 74.0060. That was the painstaking reality for the pioneers of computing.
So, how in the world did we solve this? Let's dive into the brilliant solution that saved programmers from having to memorize just endless strings of numeric codes.
Instead of those raw numbers, programmers created something called mnemonics. It's just a fancy word for short, readable, and memorable words, like MOV for move or ADD for add, that stand in for a single computer operation. They're basically mental shortcuts that make the code readable.
Now check this out. This is where you can really see the transformation. That cryptic binary code we saw earlier, it becomes a human-readable instruction, MOVAL61H. Suddenly, it's clear. It tells us to move a specific value into a little spot in the processor called a register. The meaning is no longer hidden.
And that is the essence of assembly. You see, it's not an abstraction from machine code. It's a direct, symbolic representation of it. This was a huge breakthrough, first developed way back in 1947, and it allowed programmers to write code using simple commands that mapped directly to what the hardware was doing.
Of course, the computer still needs its ones and zeros. So how do you bridge that gap? Well, you use a special utility program called an assembler. Its only job is to take those human-readable mnemonics and translate them right back into the pure machine code the processor can actually execute.
So the whole process became this simple three-step dance. Step 1, you write your code with mnemonics. Step 2, the assembler translates it. Step 3, the computer executes the final machine code. This was a revolution. It freed programmers from all that tedious, error-prone work, and productivity just shot through the roof.
But, like always in tech, this elegant solution created a brand new problem. You might call it the Tower of Babel of computing. See, the issue is that every processor out there speaks a slightly different dialect of machine code.
And this is the crucial limitation. Because assembly is tied so directly to the hardware, a program written for the Intel chip in your laptop has to be completely rewritten to run on the ARM chip that's probably inside your smartphone. This lack of portability was a huge drag on how software could be shared and developed.
And that limitation is exactly what drove the next big leap in programming. Starting in the 1950s, high-level languages like Fortran and COBOL started showing up. Their magic was that they could be compiled to run on different computer architectures. So by the 1980s, assembly had shifted from being the main way people programmed to a much more specialized niche tool.
Computer scientist Fred Brooks really hit the nail on the head here. The point is, languages like C, Python, and Java offer just enormous gains in productivity. Programmers could suddenly focus on the logic of their app without worrying about the gritty details of the hardware. And that's what really cemented the dominance of these high-level languages.
So, if high-level languages are so much more productive and portable, is assembly just a historical relic, a ghost from computing's past? Not at all. It's still very much alive, and believe me, it is absolutely essential.
Assembly is still completely irreplaceable in any area where code has to talk directly to the hardware or be optimized for just absolute maximum speed. I mean, think about the very core of your operating system, the drivers that make your graphics card work, or the embedded systems in your car or a medical device. All of these things still rely on assembly for their most critical tasks.
So what is it about assembly that gives it this enduring power? In an age of incredible abstraction, why do we still need a language that gets this close to the hardware?
Well, the trade-off has always been pretty clear. High-level languages give us convenience, safety, and portability. Assembly language, on the other hand, gives us raw power, precision, and the ultimate control over the machine. It's kind of like the difference between driving an automatic car and being a Formula One engineer tuning the engine by hand for peak performance.
And there's a brilliant example of this balance in one of the world's most important software projects, the Linux kernel. I mean, this is the foundation for everything from Android phones to the world's biggest supercomputers.
Now, while over 97% of that kernel is written in the high-level language C, that critical 2%, that little slice written in assembly, it's irreplaceable. It handles the most fundamental tasks, like the initial system boot up and the core management of the processor's hardware. The truth is, without it, the other 97% couldn't even run.
And this is really the key takeaway. It's not about choosing one over the other. Assembly is the essential bridge. It connects our abstract software with the physical reality of the silicon chips. It allows programmers to access specialized processor instructions and control hardware in ways that high-level languages, by their very design, simply can't.
And that leaves us with a pretty fascinating question. As our technology gets more and more complex, with layers upon layers of abstraction, the need for a direct, unfiltered line to the hardware, well, it may actually become more important than ever. It really seems like the language of the machine is here to stay.